So for selection sort, you select the smallest element and swap it into position. So it's kind of like bubble sort, but there's fewer swaps. The algorithm makes use of a flag or an index variable to hold on to this place of the smallest integer. Okay, and then you'll pass through it, putting that smallest number into place. Let's see an example. Here's your list: 12, 34, 18, 5, and 7. Your flag starts at 0, so that 12, right, you're only seeing one number, 12 is going to be in the right spot. I might have misspoke there. So we begin looking through our numbers, and these slides have really subtle coloring. I wish I'm going to tell Mr. Simon to choose another color on the number you're examining. So we start at position 0, then you move on to position 1. Currently the flag is 0 because 12 is the smallest number I've seen. Now I'm looking at 18. You ask yourself, is 18 the new smallest number? Nope. I go on to 5, and yep, I found a new smallest number. Position 3 in this array, this list, is now the smallest number. So I update my flag. Then you still got to check 7. Is 7 less than my current flag? Nope. So my flag remains 3. I've passed through my array once. After one pass, I found that the smallest number is 5. So, yep, that's what I said in words. And so then I swap it into position. 5 is now in the right spot. Okay, you've selected the smallest number and placed it into its correct position. We repeat this process. So you have this idea of like a sorted part of your list and an unsorted part. And you'll begin again. Instead of starting at position 0, because it's already sorted, start at position 1. Begin that comparison. Find the spot for that smallest number. So the flag is currently at position 1. That's 34. You look at 18. You see that it is smaller, so you update your flag. You find 12. You see that it's smaller again, so you update your flag. You look at 7 and see that, it is yet again even smaller, so then you update your flag once more. When you hit the end of your array, you perform the swap. 34 and 17 switch, and now 5 and 7 are in the sorted positions, right? They are in the right spots. Now we have to process 18, 12, and 34. Again, we begin looking, start at position, I think this one should be really position, start your flag at 2. Yep, start at 2, see that it's 12, okay, update it to 3, see 34. The flag position is done, we begin to swap, 12 is now in the right spot. Start at position 3, find the smallest, yep, position 3 stays the same, and after this pass, our numbers are sorted. That's selection sort, yeah? So in contrast, we have insertion sort. So this one is similar, but when we compare them side by side, you should be able to describe and see the difference. Insertion sort starts by sorting the first part of the list. The first unsorted part is inserted into the sorted part of the list. We need to see examples. The words don't do it justice. So we have that same list, 12, 34, 18, 5, and 7. So a single number by itself is sorted. So position, or the 12 in the beginning, we'll count that as sorted. And then we'll store the first number after the sorted section in a temporary variable. So here, the next, the part that we're looking at is 34. So we ask ourselves, compared to 12, where should 34 be? Should it be on the left or the right? Do you need to slide 12 over? And notice, we aren't considering 18, 5, and 7 right now. We're trying to sort just the left part, these two numbers. Fix those first. So you insert 34 to the right of 12, because it's bigger. So our sorted part of our list right now is 12 and 34. We get one number and think about, okay, where does 18 go? Do you need to move any of 12 or 34? Where should you insert 18? You need to insert 18 between 12 and 34. So you need to slide 34 over. Yep, so it goes there. And at this point, we have 12, 18, 34 sorted. We take one more from the unsorted part of our list. We are now holding on to the number 5. We ask ourselves, where do we insert 5 in my sorted section of the array? It needs to be on the left of 12, so everything needs to be slid over. Not there, but over here. We say sliding because the algorithm does like shift things over until it finds the right spot, and you'll see it in the little animation we have. Lastly, where do we insert 7? We need to move some numbers over. Yep, 34 is too big, so swap it to the left. 18 is too big, move it over. 12 is too big, move it over. 5. It is smaller than my 7, so it must go here. Insert 7 between 5 and 12. Ta-da. Alright, so these animations will highlight the difference between selection sort and insertion sort. When describing them with words, they look the same. These pictures, you can see the difference, and we'll maybe watch it like 2 times through. Selection sort, the name comes from selecting the smallest number and placing it in the right position. Insertion sort has like that sorted, unsorted idea. Where do you place? You're inserting numbers into their right spot, one number at a time. So stare at one, look at a red block or red number, see if you can predict where it will go. Okay. Focus on the red block. The greens are the comparisons, yellows are the sorted parts of the list, the blues are the unsorted parts. Once more through, and then we'll move on to the next slide. I find this one most helpful. Okay, watch where the red happens. Okay, with the yellow and the blue in insertion sort, you really see the two halves, right? The sorted part and the unsorted part of your array. Selection sort, one by one, has to do those comparisons. You're always selecting the smallest one and placing it in the right position. All right, cool. We have one more video to watch with this little odd-looking robot fellow. I hope I don't get copyright stricken. Let me turn on the sound. So I'm going to reshare my screen, as I did not turn on sound the first time. Okay, it's loading. You get to see a targeted ad to my YouTube watchings. Oh, guess not. Skipped it. Nice. Sound good?
This short-sighted robot will now demonstrate insertion sort. First, let's assume the left half of our input is already sorted. We'll now add the next element to the sorted part by moving it left until we find where it belongs. We'll compare it with its left neighbor. Since the neighbor is brighter, we'll swap. We'll continue until we find an element darker than the one we're adding. This is the right spot for it. We'll now repeat the same steps with the next unsorted element, and so on. Now let's start from the beginning. The first element by itself is already a sorted sublist. We'll extend it by adding new elements, same as we saw before. The two algorithms share some similarities. Both work in iterations, extending the sorted part one element at a time. So why did insertion sort win so decisively? Let's replay the entire match. We'll focus first on bubble sort and draw a mark on this chart for each comparison it makes. In this variant of bubble sort, the iterations gradually get shorter. It skipped the last two iterations thanks to its ability to detect when the list is already sorted and stop. But starting from a random permutation, this optimization is only likely to occur near the end anyway, so the number of comparisons is roughly n squared divided by 2. Now we'll draw the same chart for insertion sort. Insertion sort starts with the shortest iteration, and they gradually get longer, but it doesn't bother running each iteration all the way. It stops when it finds the correct spot for the newly added element, which on average happens in the middle. Therefore, the number of comparisons here is approximately n squared divided by 4. So no wonder insertion sort won. Now let's draw a similar chart for an algorithm we've shown in previous videos.
So pretty neat. That level of analysis that happens is pretty cool if you're talking about efficiency. It embeds the math with the computer science. I found it really interesting. And when you go to study it later in college, you'll understand a lot more of these, but just a little taste of how sorting can get more complicated if you're looking at efficiency. A big problem in computer science. Can you always do better? Or can you do better? And the answer is always yes. I hate it when did I hate it? I kind of did when my Chinese computer science professor asked me, like, can we do better? And you're like, yes, professor, we can. And he'd always say that, and it always feels like it was like my parent or something. It's like, dang it, Mr. Young Chan, you need to do better. Like, yes, I can do better. All right, so back to the multiple choice questions that you could be asked related to sorts. We, again, have these ideas of passes or inserted positions that could be asked of you. Notice here we have insertion and selection sort. Let's see if we can understand what's going on. So in insertion sort, that's where we have the unsorted and sorted parts of the list. Let me talk you through it. We assume that in the beginning 5 is in the right spot, it's sorted, and then okay, we have a 5 that's sorted, and then you insert 4 into the right position. It needs to be on the left of 5. Notice these numbers over here remain unchanged, 7, 1, and 2. Okay, that's the unsorted part of the list. Take a guess now on this next blank. What should be that order? You can type that into chat so I can verify that you know what's happening before clicking on to the next slide. What goes into insert pos number 2? What's the sequence of numbers? And we kind of got 2 people, I think, are you skipped ahead into position 3, I think. Yeah. Some people are a little bit ahead. So remember, we addressed 5, right? That's our first insertion. Then, in the next one, you should be thinking about, okay, where do I place the 7? It happens to be in the right spot, but you're still checking on that 7. It could have been a different number, and it could have gone like before the 4. Okay, 7 is now a part of my sorted list. 1 and 2 remain unchanged. Okay, and then for organization's sake, let me just message a break in the chat so I keep it separate. Now go ahead and try insert position number 3. What goes into those blanks? Type that sequence into chat, please. There we go. Cool. So for the people that answered, you see that now we are looking at 1. Where does 1 go? Where do we insert it? You need to insert it before the 4, so everything gets slid over. Very good. So it begins with 1, 4, 5, 7. 2 is the only number remaining after this pass in our unsorted portion. And lastly, I don't need to ask for this, you insert 2 in the right position, it becomes 1, 2, 4, 5, 7. Okay, changing gears, for insertion sort, before showing you the first step, can you give me in chat the sequence of numbers after insertion sort? What does it look like after the first pass? What goes here? Remember, you select the smallest number, swap it into the correct position. Okay, selection sort. Okay, I think one student has gotten it correct right now. Other people appear to be doing an insertion step. There we go. Good job, Emmy. Stanley, I think you got it. Travis, you got it. Langdon, you got it. Emily, you got it. Okay, so the first couple responses, it appears to, let me just show you now. So the answer should be 1 and 5 switch positions. 4, 7, and 2 were untouched, so they stay in the same spot. Selection sort looks for the smallest number, places it in the right spot. Okay, so 1 and 5, when I say place, it's really swapping it. When you see 1, you need to swap it with 5. 4, 7, 2 remain unchanged. So try it once more. After the second pass, what will that sequence of numbers look like for selection sort? What's the next smallest number? Perform a swap. And type out that sequence of numbers. Good. Langdon, good. Good. we are reaching more of a consensus now. Nice. Everyone's numbers look the same. Yes. Very good. So now we swap 4 and 2 because 2 is the new smallest number. And the rest of the array gets copied on down. Right, 7 and 5 remain unchanged. Again, we write a break. And then third pass, what will that array look like when your 3 passes through? What's the next smallest number? What gets swapped? Very good. Nice. Okay, clicking on, you see that 4 and 7 get swapped. And the fourth pass, it's already sorted. You still look at 7, put it into the right, or look at 5, I mean, see that it's in the right spot, and we're done. So now that we've gone over selection sort and insertion sort, you should have some kind of way of remembering it, the difference. Their namesakes could help you. With selection, there's the swap keyword that is there, and the smallest number. The insertion sort, think about the two halves, sorted and unsorted arrays. And you're sliding. I wish they weren't all S words. So work on, please, C through F. Open that Google Doc, type in those numbers. If people want to check over the first one in the solutions on APCS Lowell, you can. I'll give you some in-class time to work on it, and please ask me questions if something doesn't line up. Maybe you should do 1 in selection, 1 in insertion to try it out. How did we do? Do you have any questions? Okay, so yes.
Can I ask a question?
Yes, please.
For the selection sort,
Yes.
if the minimum number during the pass is in the right place, does it just like stay the same?
There is no swap that occurs if that number appears to be in the right spot. Which one were you working on, C or D?
D.
D.
But I guess it's in C too.
It occurs, right? Like 7. 1, 9, 8, 4, 5, 7, 1, 4, 8, 9, 5, 7, 1, 4, 5, 9. I think that's the 8, right? 8, 7. Yeah, so that passed, that there would be no swap that occurs and that sequence remains the same. Yep. Cool. So that would be it for today's class. Please make sure these things are finished so you have like no work to do and just turn it in if you finished it. And formally, I'll dismiss you all and stop my recording.